So today's talk is a bit anti-thematic for this conference. The conference, of course, is about using ultraproducts or the equivalent non-standard analysis and mathematical proofs. Today I'll be discussing removing the non-standard machinery from such proofs. Well, of course, there's nothing new about that kind of thing, but we'll talk more about that later. Some of the main motivation for this talk comes from this book, Hardy's Orders of Infinity, which is a survey from 1910, in which he discusses a variety of results from mainly from the 19th century about increasing sequences of numbers and various orders on the collection of increasing sequences of numbers. In particular, he gives results by Jacques Hadamard and Paul de Bois-Reymondand, which, when you look at them carefully, turn out to be very, very similar to results to properties like saturation and permanence. This monograph, by the way, is full of delightful tidbits of interest to logicians. For example, he proves that the logarithmic exponential polynomials, which is the closure of 1 and x under logarithms and under taking p to the q, where p and q are in the family, are linearly ordered under eventual domination. And that was used, for example, by Ehrenfeucht in his proof that the exponential polynomials are well ordered. And especially if you do a reverse citation check on the Automar result that we'll be stating later, you'll find that it's been used quite frequently by logicians. Right. So as a general outline of the talk today, I'm going to talk a little bit about things called asymptotic fixed points. I'm going to give a non-standard proof. I'm going to give another non-standard proof, and those are just going to be sketches of proofs because that's not the main import of what we're doing now. And then finally convert the second non-standard proof into a standard proof using these results from 100 years ago. Some notation and assumptions for today. We're always going to be working on a complete metric space X with metrics D. T from X to X is going to be a continuous function. And we say that a point in X is an iterative fixed point for T, provided, first of all, it's a fixed point. And second, if you take any other point in X and look at its orbit under T, so the iterates of X under T, it eventually tends to X infinity. Note that you're an iterative fixed point if and only if for any x, y in the original space X, and for any infinite I and j, so that's the infinite integers, positive integers, the distance is infinitesimal. And of course, the reason for that is if you just let x equal y in this criterion, what it says is the orbit is Cauchy, and there it converges to some x, since we're assuming that x is complete. If you take any x different from y in x, what it says is the two orbits converge to the same thing. And of course, if x infinity is one of these iterative fixed points, that says, well, that's infinitely close to t of t to the I x, because for I infinite, because t is continuous, and that's t to the I plus 1 of x. And again, since the orbit t to the I x converges to x infinity, that's infinitely close to x infinity. So it's trivially seen to be a fixed point. Okay, this is all an easy exercise in non-standard analysis. And everyone knows the statement and proof of the Bonding fixed point theorem. Suppose that for any x and y in x, the distance between t of x and t of y is less than or equal to r times the distance of x and y for some fixed r less than 1. So we look at the orbit of a point x under t. This image picture is not to scale. And then between any two of them, the distance when you go to the next set is less than or equal to r times the distance before, which means that at the nth level, the distance between 2 to the n of x and t to the n plus 1 of x is less than or equal to r to the n times the distance from x and t to the x. Then, of course, t has an iterative fixed point, and the proof of that is, again, quite easy. It's just the observation that the distance between t to the I of x and t to the j of y, if I and j are infinite, is less than or equal to r to the min, r to the min of I and j over 1 minus r times the distance between x and t of x. This is finite, and this is infinitesimal. Okay, so we all know how to do that. In 1969, the mathematicians Boyden and Wong generalized this in an interesting way. They said, first of all, the contraction depends, so phi is measuring the contraction here. The contraction might be different depending on the distance. So the contraction depends a little bit on the distance. And second, the nature of that contraction is that it's an upper semi-continuous from the right function. And in non-standard terms, upper semi-continuous from the right means that the right halves of monads get pushed down. If you start with a standard element S, and we look at the right monad, what phi does is pushes us down, or maybe infinitesimally close to S. It doesn't push anything up, but it could push it more than infinitesimally down. And of course, this is a slight change from the notion of upper semi-continuous in general. In the non-standard characterization of a function being upper semi-continuous means that if you look at the monad of a standard point, phi takes that monad less than or equal infinitesimally close to the standard point. And here, for reference, is an example of a function which is not upper semi-continuous, but it is upper semi-continuous from the right. The stuff a little bit to the right of S actually gets pushed to be a little bit less than the function at S, but the points a little bit to the left of S get pushed here, which is bigger than the function's value at S. The examples we see today will actually just be upper semi-continuous. And they said that was enough to get an iterative fixed point. In 2003, Kirk conjectured the following, and he proved it, an asymptotic version of the Boyden-Wong theorem. And the idea here is that the amount of the contraction is not only a function of the distance, but it's also a function of the iterate. So the distance between t to the n of x and t to the n of y is not less than or equal to the nth iterate of phi at d of x and y, which it would be in the Boyden-Wong case, but it's less than or equal to some phi sub n of d of x, y, where phi sub n for large n looks like phi. Phi sub n converges to phi uniformly on the range of the metric. And phi is upper semi-continuous, so phi satisfies the conditions of Boyden-Wong. Well, to prove his result, Kirk required a couple of additional conditions. First, that phi and phi sub n are continuous. Those actually don't play much of a role in his original proof, so they're really not big requirements. But also that t had a bounded orbit. That is, for some x, the iterates of x were all bounded by some number. And this is a condition which in recent years has been eliminated, and we'll talk more about that a little bit later. This result spawned sort of a small industry in asymptotic fixed point theorems, and it also attracted the attention of the proof mining community, notably Philip Gahardy and Ivan Breiside, who have come up with proofs of the result which give quantitative information on how quickly the iterates converge. Okay, so the question that occurs naturally to somebody doing non-standard analysis is, can this theorem be proved by applying Boyden-Wong to a suitable space? And the answer is yes. You can give a proof using non-standard hulls. So how do you do that? Well, first you prove that there's a bounded orbit, or you take it as an assumption. So in the case of Kirk's original theorem, it was an assumption. Now, if there's a bounded orbit y, that means in particular that y is closed, or star y is closed under any power of the function t, which is nice. In particular, we can work with an infinite power of the function t to the h. And if we take this star y, which is a subset of the finite elements of y, and so we can form the non-standard hull. So if we take the non-standard hull y hat of y, and then take the function t of it, t to the h, that induces a function which we'll call hat t to the h on the non-standard hull of y. And then we have to show that this satisfies the conditions of the Boyden-Wong theorem, namely that it's less than or equal to the phi that's given. And that's actually not so difficult. I'll say something about that in a minute or two. And that proves that in y hat, there's a unique iterative fixed point, x infinity hat, let's say, for this t to the h hat. So this part's actually pretty straightforward. Now, a priori, this x infinity, or the x infinity hat is in y hat, so x infinity is a priori only in star y. It can be used to find a point y infinity in x, which is infinitely close. You just basically take the point in x which is closest to this x infinity, and use the fact that x is complete to get a Cauchy sequence. So you get a sequence in x approaching x infinity, and by completeness you can find a limit y infinity and show that's infinitely close to x infinity. So that's also straightforward. Slightly tricky is to show that this y infinity is an iterative fixed point for t on x. It is, of course, approximately an iterative fixed point for t to the h on y hat, but that's not good enough. We want to get this h and replace it with just a 1. And that takes a little bit of work. But the rest of this, including the setup, is really the sort of thing that you could even put into as an exercise. Graduate course in non-standard analysis. It's a very natural way to try to extend the Boyden-Wong theorem, and it works without very much difficulty. This last step is a little bit tricky. Now this is assuming there's a bounded orbit, and to really get the complete proof, you want to somehow eliminate this assumption. And in the course of proving that, in fact, there is a bounded orbit, and in fact, if there's a bounded orbit, all orbits are bounded, but in the course of proving that there's a bounded orbit, one was able to come up with an actually easier, at least more elementary, proof of Kirk's theorem. This proof is more elementary. For example, it doesn't use non-standard hulls, but in many ways it's less natural. So let's, as we already talked about n infinity being the infinite natural numbers, let's introduce the notation I double less than j if j minus I is infinite, so if j is infinitely larger than I. Given two hyperreal numbers, let's say one is less than or approximately equal to the other if it's either less than or equal to the other or approximately equal to the other. And notationally, I will usually be dropping the stars on things. And we can start with a couple of useful inequalities. So let's suppose we take x and y in star x, so they could be non-standard x and y, and an infinite h. Then the distance between t to the h of x and t to the h of y, well, by hypothesis, is less than or equal to phi sub h of d of xy. This is just the transfer of the condition from the original result. And we're given that the phi sub n's converge uniformly to phi on the range of d, and that means, by the usual convergence criterion, that this is infinitesimally close to phi of d of xy. And by hypothesis, phi of d of xy is less than d of xy. So I'm applying this to non-standard elements, so we're talking about phi being star upper semi-continuous, and phi, this inequality being a star inequality, right? This should really be star less than. And so this could just be infinitesimally less than d of xy. But if we started with a couple of finite guys, d of xy being finite and not infinitesimal, well, we still get to here. But now we can take the standard part of d of xy and ask what's phi of that. Of course, this will be the standard phi of the standard d of xy, and the condition of upper semi-continuity tells us that that's less than or infinitesimally close to phi of the standard part of d of xy, and that's strictly less than the standard part of d of xy. So this is strict and not infinitesimal. Of course, that's if standard part of d of xy is not equal to 0. And what we've proved is this. If we take any two distinct elements of star x and an infinite integer, then first of all, the distance between t to the h of x, t to the h of y is less than or infinitely close to the distance between x and y. And if this d of xy is finite and not infinitesimal, then the inequality is strict in the sense that if we take the standard part of both sides, it's less than. So this becomes less than and not infinitesimally close to d of xy, in other words. And that's quite useful. And in particular, if you think back to the non-standard hull argument, this tells us that t to the h is S-continuous on star y. This is assuming, again, that star y that y was bounded. So that's well defined. and continuous. So that's what we used, could use in the previous result if we were doing the whole proof of Kirk's theorem. So let's prove Kirk's theorem. First, we need a little bit of notation. So if we've got x in the standard metric space, and m is either a finite or infinite natural number, let's put r sub I as the distance between t to the I x and t to the I plus m of x. So down here in the picture, here's an orbit of x under t. Here's the finite part, and then continues on possibly to infinite part. And I want to go from t to the ix to t to the I plus m of x, and we're calling this distance r sub I. So r sub I is really a function not only of I, but also of x and of m. But I just don't want to write it down. So r sub I plus 1 is where we look at the distance between the next iterative x down here and the next iterative x I plus m plus 1 of x down there. So we want to know what happens to that distance for the fixed m as we let I get bigger and bigger. And the first conclusion is that if I is infinitely less than j and r sub I is finite and not infinitesimal, then r sub j is strictly smaller. The standard part of r sub j is strictly less than the standard part of r sub I. So as we move out, if we move infinitely far along this orbit, we decrease by a non-infinitesimal amount. Second, if I is infinite and m is finite, so if we're only looking at finite differences here, for a little red bracket there is just a finite number of m's, then once we get out to infinity, they're infinitesimal. The third part of the lemma says that in fact, we don't need that m to be finite, but as long as we know that the r sub I is finite. And finally, we get that the orbit is bounded. And that'll be enough to prove the theorem. We'll get back to that. Okay, and let's just real quickly see why a couple of these anyway are true. I don't want to go into full detail. So let's look at the lemma again. The first conclusion is that if we have I infinitely less than j, then r sub j is less than and not infinitely close to r sub I. And that's really just a restatement of that lemma. So I'm not really going to say much more about that. Second one is far more interesting. So we want to show that if we go out infinitely far and just look at the difference between t to the I of x and t to the I plus m of x, where m is finite, then we only differ by an infinitesimal amount. And the proof of this is where we're going to use saturation. So the first step is to find a sequence of infinite integers indexed by omega 1, which are increasing, where each one is infinitely larger than the one before it, and where they're all less than the fixed I. So starting with an I0, which is infinite, we want to find an I0, I1, I2, and so on, an increasing sequence indexed by omega 1 less than I. Or so we can find a copy of omega 1 inside the infinite interval, well, any infinite interval ending in I. And that's actually a pretty straightforward exercise using omega 1 or alpha 1 saturation and a little bit of induction. I'm not going to go through the details on that, but it's sort of the key fact that we're going to have to reproduce when we get out of the non-standard universe. And it's a fact about what kind of order types we can find inside the ordered set of the infinite natural numbers. Now, if we look at the sequence of these standard part of r sub I sub alphas, right, we know that r sub I sub alpha, that's the distance between t to the I sub alpha of x, t to the I sub alpha plus m of x, and that's less than or equal to the distance between x and t to the m of x. That's by the lemma zero. So it's bounded. This is a finite, because we're starting with a finite x, and m is finite. So these things are all bounded by the one standard number. So that's out here somewhere. We can start with I0. And so this increasing sequence becomes a decreasing sequence between 0 and, well, it's in the non-negative reals, but between 0 and standard part of r sub I 0, ordered by omega 1. And that tells us what? That tells us that eventually it's got to stop because there is no strictly decreasing sequence of order type omega 1 in any standard real interval. So this decreases until some r sub I alpha, standard part, equals 0. But then, of course, r sub I, standard part of r sub I, also has to equal 0, this guy. And therefore, r sub I is infinitesimal. It's a very external argument using the order structure of the non-standard integers. Keep that in mind for later. Okay, so the third step is we want to somehow eliminate the fact that m is finite. And so what we do is we take one of these r sub i's and we shift it by a finite amount. So this r sub I is still a function of, well, the original x, and it's a function of I, and it's also a function of the m. But now the possibility is m is not finite. That's what we're looking at here. So we look at the same r sub I and shift it, in this case by a finite amount. In the picture I've shifted it by 4. Well, no, I haven't. So in this case I'm looking at, so in this case I've shifted it by 4. And so here's r sub I plus 4 and here's r sub I. And this distance here is the distance between t to the ix and t to the I plus 4 of x, which we know from 2 is infinitesimal. Similarly, this is infinitesimal. The distance between this point and this point is infinitesimal by 2. So if we look at the difference between r sub I plus n and r sub I, shifted r sub I for a finite amount, for any finite amount, it's infinitesimal. And now we can use our favorite permanence principle. Usually call this one Robinson's sequential lemma, that since this internal difference is infinitesimal for all n, there has to be standard n, there has to be an infinite n where it's still infinitesimal. But then if r sub I was not infinitesimal, r sub I plus n, the standard part, would be strictly less than r sub I. But we've got that the standard part of r sub I equals the standard part of r sub I plus n. But on the other hand, by the earlier result, we know that the standard part of r sub I plus n, since n is infinite, is strictly less, and that's a contradiction. Okay, therefore, r sub I is infinitesimal. And finally, for the proof of 4, that there's a bounded orbit. So otherwise, we can define a sequence in the following way. We can start by looking at the zeroth element of our orbit. So we let k sub 0 be 0. And then k sub n plus 1 is the least k bigger than k sub n, such that the distance between t to the k of x and t to the k sub n of x is bigger than or equal to 1. Right? If this sequence is not bounded, if we stop anywhere and continue from there, eventually we have to have a distance bigger than or equal to 1. So we go from x to t sub k1 of x. So this x is the same as t k0 of x because k0 is 0, until we're just, first time we get bigger than 1. Second time we get bigger than 1. Third time we get bigger than 1, and so on, which means that the point before, the distance between x and t to the k sub 1 minus 1 of x is strictly less than 1. So we take the sequence and we extend non-standardly. So we let h be infinite. And the distance between t to the k sub h of x and t to the k sub h plus 1 minus 1 of x, well, that's less than 1, but that's less than or equal to the distance between t to the k sub h of x and t to the k sub h plus 1 of x. But we also know that the difference between these two guys must be infinitesimal by the previous step. Therefore, the distance between t to the k sub h of x and t to the k sub h plus 1 of x must be infinitely close to 1, and that's a contradiction. Because what we've shown already is that these things can't be, they either have to be infinitesimal or infinite. They can't be something in between. And that proves that. Okay, so let's return to the lemma we were proving. And this lemma does give us that the orbit is bounded. But a little observation tells us that we actually get more. When the observation is that this lemma still holds if replace the distance between tix and ti plus m of x by the distance between ti of x and ti plus m of y, where x and y are elements of the original space x. And that's just by going back through the proof and checking that the steps still work. And that observation gives us the fixed point theorem, right? Because if x and y are in x and I and j are in star n, then the distance between t to the ix, t to the j of y, less than or equal to the distance t to the I of x, t to the I of y, plus the distance between t to the I of y, t to the j of y, and both of these are infinitesimal. If we assume that j is bigger than I, this is the same as the distance between t to the I of y and t to the I plus m of y, where m equals j minus I, for example. And so this whole thing's infinitesimal, and that proves that there's an iterative fixed point. Okay, so that's the non-standard stuff. Now we ask, can a standard proof be extracted from this one? And the answer is yes. Okay, now look, it's not that hard often to get a standard proof from a non-standard one. For example, if we prove something using internal set theory, then Nelson's algorithm lets us algorithmically convert it to a standard proof. If we have a proof using infinitesimals in a usual epsilonic way, then of course that can usually be easily converted to one with epsilons and deltas. We've been doing that for a couple of hundred years, ever since the delta epsilon method was brought in as a substitute for infinitesimals. But if we have a non-standard proof, which is essentially external, that means, for example, one that uses non-standard hulls, or in this case, it's essentially external because we're looking at the order structure of the non-standard integers, then it's usually not so simple. And that's where these results come into play. Okay. So the first one is due to Jacques Hadamard. It appears in the monograph of Hardy that I mentioned before. And it says that if we've got functions phi sub n, now I haven't defined this ordering yet, I will, but if we've got sequences of real numbers phi sub n and phi, which are increasing but strictly bounded by phi, then there exists some f, also a sequence of non-negative real numbers, which can be squeezed in between these phi sub n's and capital Phi. Similarly, if we've got psi's that are decreasing but are always bigger than this phi, we can squeeze some f in there. And more generally, if we've got an increasing sequence of phis like this and a decreasing sequence of psi's like that, we can squeeze an f in there. And again, I'll define this notation in a minute, but we're looking at increasing sequences of real numbers under a domination ordering. This was proved by Hadamard. Hardy says that Hadamard, in turn, was generalizing a proof of Paul de Bois-Reymondand. Now, this notion, if you're a non-standard analyst, looks immediately familiar. This looks like Aleph 1 saturation. Okay. And it's not a new notion in logic. So for example, Hausdorff talked about A to 1 sets, which were linearly ordered sets that had exactly this kind of property, this kind of order structure. But for us, it looks very much like LF1 saturation. Similarly, this theorem of Paul de Bois-Reymond, which is that if we've got a collection, a sequence of sequences of real numbers, each of which decreases to 0, so delta sub k is delta sub k of n is a sequence that goes to 0, and that's for all k. Then, in fact, we can find some increasing sequence. That's what this is going to be, is an increasing sequence of natural numbers, so a subsequence of the natural numbers, so that delta sub gamma of n equals 0. And this is often appears as an exercise in introductory analysis books, but this was a result of Paul de Bois-Reymond, which also appears in Hardy. And whereas this first one is kind of like LF1 saturation, this one is very much like a permanence principle, so like the Robinson sequential lemma. And these are exactly the tools that are going to let us remove the non-standard content from the last non-standard proof. So let's define some notation. We're going to let this fractor n be the set of sequences of natural numbers, and fractor n infinity will be the set of increasing sequences of natural numbers. For any two such sequences, we say that S curly brackets t, if as sequences t of n over S of n goes to infinity, or the way I've written it here, S of n over T sub n. This should be fractor S, or a bold-faced S. S of n over T sub n goes to 0. So if the ratios go to infinity, of the bigger one, the ratios go to infinity. Okay. A slightly milder order is T should still increase faster than S, but if the difference goes to infinity. Similarly, if we let fractor R be the set of all sequences of non-negative real numbers, and R infinity be the ones that go to infinity, for any two such sequences, remember when I write this, I mean A is a function of n, and B is a function of n. We say that A is less than or infinitely close to B, if for all epsilon, A sub n is eventually dominated by B sub n plus epsilon. A sub n is less than and not infinitesimally close to B is if the B sub n's are eventually bounded away from the A sub n's by some epsilon. These will almost always be applied to sequences that actually go to infinity. We say that A is infinitely close to B. Well, it's just the same notation, but it doesn't mean that for infinitesimals. If the difference between the A sub n's and the B sub n's go to 0, A is not infinitesimally close to B if the lim inf of the difference is bigger than 0. In other words, if B sub n is bounded away from A sub n. These are not negations of each other. But that's convenient notation to have. We say that a sequence is finite if the same thing is saying it's bounded. And we say that a sequence is not infinitely close to 0, meaning that 0 is less than an infinite and not infinitely close to A. In other words, A is bounded away from 0, is eventually from 0. And it's important to keep in mind these are all sequences, but we're writing them as if they're just numbers in some system. Now the new lemma, which is the equivalent of what we called Lemma Zero, remember what Lemma Zero was. It said that in the world of the infinitesimals, the distance, if we go out infinitely far in the orbit between h and y, is less than or equal to the distance between h and y, or infinitely close to, and that it strictly decreases. The corresponding lemma here, well, we have to be a little bit careful. We can't talk about x and y in star x. That's not a concept that really exists anymore. So we replace it by looking at t to the s of x and t to the s of y, where s is some increasing sequence. So this lemma, the difference between t to the t of x and t to the t plus m of y, remember these are sequences. This bold-faced t as a superscript is a function of n, and so this is actually a sequence. is less than or equal to this sequence corresponds to the first step in Lemma Zero. And similarly, the third step here, which says that if you've got a bounded bold-faced m, and the distance between t to the s and t to the s plus m is not infinitesimal, then it strictly decreases when you change from s to t, is the corresponding thing here. And I don't want to prove both of these. Let's prove one. So now what happens to the lemma 1 from the earlier non-standard proof? Well, it turns into something like this. So now we're going to have s and t be increasing sequences of natural numbers, or possibly the constant 0. And m is just some sequence of natural numbers, might be increasing, might not be, might be unbounded, it might not be. So let's let x and y be elements of our metric space. And let's now write r of sm as being the distance between t to the s of x and t to the s plus m of y. And remember, this is a sequence. Then the corresponding steps are, if s is this slightly milder inequality less than t, and this r of sm is bounded away from 0 but bounded, then r actually decreases. And if m is bounded, then this r actually goes to 0, right? Because that's what this notation means. If our r is bounded, then in fact it goes to 0. And then finally the orbit is bounded. And let me just say where these Hadamard and Bois-Reymondand results get used. So let's just talk about this one. This first one is just lemma 1 prime, just like the corresponding part of the original lemma, 0 prime. Corresponding part of the original lemma 1 was from lemma 0. For 2, well, we can assume that our sequence m is bounded by some number m, and let's put, I don't know, w be something bigger than, so 1 plus, let's say, the max for all m less than or equal to big M of the distance between x and t to the m of x. So this is going to be some kind of an overall bound for our r's now. And let's let, this is by Hadamard, t to the alpha be a sequence in Proctor n infinity, alpha less than omega 1, where t to the alpha is this order less than t to the beta, and this order less than s, whenever alpha is less than beta. So let's let this be the embedding of omega 1 into the ordering, into this curly less than ordering on the sequence space. And this is what uses the Automar theorem. Now, we know that r of t to the alpha m is less than or infinitely close to r of 0 m. That's by the earlier lemma, and that's bounded by our w, because this bold-faced m only is allowed to take these values between 0 and capital M. So this is a sequence, and this represents distances, and the distances it represents are distances that look like that. Okay. Therefore, either r of t to the alpha m is approximately equal to 0, which means goes to 0 for some alpha, or we have a strictly decreasing sequence of sequences in this ordering. R of t to the beta m is less than and not infinitely close to r of t to the alpha m, for alpha less than beta less than omega 1. But in the latter case, if we just replace this sequence with its lim sup, that becomes a strictly decreasing sequence of real numbers in 0 w with order type the opposite of omega 1, and you can't have that. Okay. So we must really have this, and that implies r of s m goes to 0. So this is very much the analog of the standard proof. It's almost the same argument, or the non-standard proof rather. It's almost the same argument. And we can do the same for step 3. We want to show that if one of these r of sm's is finite, then in fact it's got to be infinitesimal. And we can do the same sort of thing that we did in the non-standard case. For k, a finite natural number, we let delta of k be the difference between r of s plus k. Again, s is a sequence, k is just the positive number, and m minus r of s m. Remember what this is. This is the distance between t to the s plus k plus m of x, t to the t to the s plus k of x, and t to the s plus k plus m of y minus d of t to the s of x to the s plus m of y. And this goes to 0 as n goes to 0. Remember, these are all functions of n. These are all sequences, etc. And that goes to 0 by step 2. And then we use the Bois-Reymondand Theorem. There exists, we'll call it gamma, n in infinity, such that delta of gamma of n goes to 0 as n goes to infinity. And that tells us that our s plus gamma m minus r of s m goes to 0. But r of s plus gamma m should be less than and not infinitesimally close to r of sm, unless r of s m goes to 0. And that's what we wanted to prove. And 4 is just like the non-standard case. Well, that's just about everything I wanted to say, probably more detail than I really should have done. But I wanted to show you that, that these tools from the 19th century, fantastic tools about sequences, can be quite useful in taking even external style non-standard proofs and standardizing them. Whether we really want to do that or not, I don't know. Most of us in this audience are quite comfortable, I think, working with infinitesimals. And of course, it's a lot easier and more natural to work with the infinitesimals. But there exist people who are not so crazy about them. And this gives us an option for certain sorts of results for those cases when we really, really want to make our proof standard. Anyway, that's it for today, and thanks for your attention. Bye.